Millions of automated coding tasks are executed every minute in modern software environments. From low-level debugging to the generation of entire test suites, the sheer volume and velocity of machine-generated code is staggering. To manage this workload, the standard industry practice is to route every prompt through a single, highly capable frontier language model. While this monolithic approach allows model providers to prioritize predictable scaling, developers have different priorities. They require task-level quality and cost efficiency. When we evaluate a diverse stream of specialized coding tasks, a consistent reality emerges. No single frontier model dominates every category. This heat map compares 8 leading frontier models across 9 specific coding dimensions, including algorithm design and code completion. Claude Opus 4.6 achieves the highest general average across the board, but a closer look at its individual scores reveals specific blind spots. In the domain of algorithm design, GLM5 possesses an 86% relative advantage over Opus 4.6. For test generation, QN3 Max takes the lead, outperforming the baseline by 111%. Across these 9 dimensions, 5 completely distinct models claim the top spot, depending entirely on what specific type of code is being written. This creates an immediate operational challenge. Selecting the right model for thousands of incoming tasks is impossible for a human to do manually. The solution is an automated routing mechanism, a system that analyzes an incoming task and instantly dispatches it to the model best suited to solve it. Treating Agentic AI as a monolithic provider problem is inefficient. Optimization requires dynamic per-task model routing. The most intuitive approach to building this router is asking a highly capable language model to act as a zero-shot dispatcher, relying purely on the text of the incoming prompt. This chart tracks performance scores from an ablation study comparing a standard Claude 4.6 vanilla router against an idealized Oracle, a theoretical upper bound that perfectly selects the best model every time. The zero-shot vanilla router scores only 41.41%, leaving a massive performance gap between its decisions and the optimal upper bound. But when we feed that exact same LLM router historical performance statistics for that specific task dimension, its accuracy jumps to 47.74%. This 15.3% leap identifies the actual source of the performance gap in automated routing. The performance bottleneck in AI routing stems from an information deficit rather than a lack of reasoning capability. A router cannot succeed without execution-grounded historical context. To address this information deficit, current industry standards have evolved through several iterations. The first attempt used static heuristic routers. These rely on hard-coded rules to map specific task keywords directly to specific models. But hard-coded rules shatter when faced with complex prompts or edge cases where keywords overlap. This led to the development of static trained policies. These systems utilize machine learning classifiers like logistic regression or route LLM. These classifiers map semantic task features directly to a model choice based on patterns found in their training data. However, static models share a critical flaw. Their memory is locked at the time of training. This creates a vulnerability to a distribution shift. When real-world tasks no longer resemble the training data, these static routers fail. To build a more resilient system, routing must be reframed as a contextual multi-armed bandit problem. This requires balancing the exploitation of models that have worked in the past with the exploration of new data to refine future choices. Solving the bandit problem requires a system capable of processing continuous updates from a living task stream. The structural solution is the CAF loop: context, action, and feedback. In the first stage, the system observes the context, including historical priors and task metadata. Second, it takes an action by dispatching a specific model from the available pool. Finally, it generates feedback by verifying the results of that decision in real time. To handle the unpredictability of production environments, a routing system must move beyond static prediction and become an actively self-evolving loop. The ACRouter, or Agentic Coding Router, serves as the functional implementation of the CAF loop. It comprises 3 modules. First, the orchestrator, the central decision node ingesting metadata, heuristic rules, and historical neighbors. It uses a cost-effective 0.8 billion parameter model to weight inputs and execute the action. The second module is the verifier, which solves the feedback problem. It evaluates the generated code using a sandbox execution environment, providing an objective pass-fail score. This feedback, along with the monetary cost of the inference, is written into the memory module. This memory uses task embeddings to group similar coding problems together, allowing the orchestrator to retrieve context for future tasks. By forcing every routed task through a sandbox and back into memory, the system ensures that every decision is informed by an expanding evidence base. The ultimate stress test for these systems lies in out-of-distribution, or OOD, agentic programming tasks. Unlike standard single-turn queries, these tasks require multi-step planning, file navigation, and iterative debugging. To evaluate success, we track cumulative regret, which measures the running performance gap against an omniscient oracle. This graph shows cumulative regret during in-distribution testing. Static models, like logistic regression, accumulate regret steadily alongside the dynamic ACRouter. But on the out-of-distribution test, results diverge. The static classifiers fail. Their regret lines climb sharply upward when encountering novel tasks. The data shows that static routers overfit to their training sets and become blind when facing novel, multi-step environments. The ACRouter avoids this because its dynamic memory absorbs these new patterns in real time, keeping its cumulative regret low. Static predictive routing is fragile. Systems will eventually collapse when faced with unpredictable real-world data. Beyond pure performance, deploying these systems at scale requires an evaluation of enterprise economics. We must ask if the computational overhead of running an orchestrator and a verifier cancels out the savings of the routing itself. This scatterplot displays the cost-performance Pareto frontier, mapping accuracy against total monetary cost. The ACRouter achieves 62.5% accuracy, beating the strategy of using the most expensive premium model. Despite its multi-module overhead, this dynamic routing system remains cheaper to run than a premium monoculture. In a landscape of heterogeneous models, optimal routing cannot be achieved with predictive shortcuts. Only by embracing a context-action feedback loop can systems continuously learn and extend the frontier of both cost and capability.